Hey guys, what's up? Today we're going to be learning about permutations, and sadly, today is the last day of lessons from me that you will get. So I want you to know that I had a great year with you guys, and you're awesome students, and I can't wait to see you for sure in the fall whenever we get back together. And I'm excited to have another year with you guys. So with that, we'll go ahead and get started today. Today we're learning about permutations. Um, and I'll tell you what that is in just a second. But first, we're going to use the fundamental counting principle to count permutations. So here's an example of a permutation. Suppose you are in charge of scheduling the order of four musical groups playing in a concert. You can choose any of the four groups as the first performer. Once you've chosen that first group, you would have three groups to choose from to go second, and so on. So the fundamental counting principle that we learned about would look like this. So you have four choices for the first group, you have three choices left for the second group, two choices left for the third group, and you'd have your last, just the single guy or single group left to perform. So if we multiplied that out, 4 times 3 times 2 times 1, we would have 24 ways to arrange that concert. So that is an example of a permutation. A permutation is an ordered arrangement of items that occurs when no item is used more than once, and the order of the arrangement makes a difference. It makes a difference. So in our example, it would make a difference in terms of how the concert is received if a musical group is the first or last to perform. Okay. Okay, so here we go. Based on their long standing contribution to music, you decide that the Rolling Stones should be the last group to perform at a four group concert. Given this decision, in how many ways can you put together the concert? So what I like to do here is put four blanks, okay, and then I just fill in the numbers. So we've already decided that the Rolling Stones are going to be last at our concert, so we have just the one choice here. And then if we go back to the beginning, how many bands do we have to pick from for our first band? There would be three bands that we could pick from that are left, right? How many bands would we have to pick from now that we've used one of those three bands? We would have two. And then how many bands are left? Just the one. And if we multiply that out, 3 times 2 times 1 times 1, we would now only have 6 ways to arrange our concert. If we look at this second example here, we're going to arrange 7 of our favorite books along a small shelf. How many different ways can we arrange the books, assuming that the order of the books makes a difference to you? Okay, so we've got 7 books. We've got 7 spots to fill them in. So how many books do we have to choose from on the first book? We have 7. That leaves us with 6 books, 5 books, 4 books, 3 books, 2 books, and then the last book would just go there at the end. And then the fundamental counting principle says that we would multiply that out. So I would definitely pull out your calculator for this. It's going to be rather large. So 7 times 6 times 5 times 4 times 3 times 2 times 1. So there are 5,040 different ways that we could arrange those books, which is pretty interesting. Think about that. That's cool. It's just 7 books. We can arrange them in 5,040 different ways. Now this 7 times 6 times 5 times 4 times 3 times 2 times 1 is a special thing. Whenever you multiply out a number and then the corresponding numbers all the way down to 1, it is called 7 factorial. And it's written like this, 7 with an exclamation point. So it's like 7 is factorial. No, you just say it's 7. You pronounce that 7 factorial. And the definition of something factorial is the product of all the positive integers of that number down through 1. And then 0 factorial is 1 is another thing. I don't know why, but it is. So that's it. All right, so what we're going to do here is we're going to evaluate these with the use of our calculator's factorial button. Now, I did not bring one of the calculators that I recommend in class to you, but I should be able to help you out. So I believe that, I might be wrong, there's either a button, I think there's a button that says PRB, and it's somewhere in this region. It's in the top right kind of area by the arrows, kind of. And if you click that, you'll see a exclamation point in there. So if you're going to do 8 factorial divided by 5 factorial, you'll hit 8, and then you'll hit that PRB button, and you will find that thing. So mine is under a different PRB, but you'll see I have it too. So you hit 8 factorial divided by 5 factorial, and it should come out to be 336. So make sure that you can do that on your calculator. If you can't, reach out to me and we can video chat and I can show you where to find it. If you look at the next one, we're just checking to make sure that you can use a calculator. So, oops, I keep hitting the wrong button. I have lots of functions here. So 26 factorial divided by 21 factorial should get 7,893,600. 7,893,600. 500 factorial divided by 499 factorial. I know what that one is. It should come out to be 500. Why is that? Well, do you remember what this means? 500 factorial means 500 times 499 times 498 times 497 times 496 times 495 times 494, so on all the way down to 1. And 499 factorial means 499 times 498, blah, 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 blah. So what does 500 factorial really mean? It means 500 times 499 times 498 times 497, which is really 500 times 499 factorial, which is over 499 factorial. Those are going to cancel each other out, leaving you with 500. So that's kind of interesting to think about. So what this one really is it is 26 times 25 times 24 times 23 times 22 times 21 factorial over 21 factorial. The 21 factorials cancel each other out, and the result is whatever 26 times 25 times 24 times 23 times 22 is. All right, objective 3 here, we're going to be using the permutation formula, and we'll talk about that in just a second. So Jimbo coaches a Little League baseball team. There are 13 players on the team. We need to choose a batting order having 9 players. An order definitely makes a difference in baseball because, for instance, if the bases are loaded and your best hitter is 4th or 5th at bat, his possible home run will drive in 3 additional runs. So how many batting orders could we form? Okay, so we have 9 spots to fill. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 13 players. Only 9 of them get to play, though. So how many players can we choose for the first batter? We have 13 players. We can choose 13 of them. How many would be left for the second batter? 12. How many would be left? 11. 10, 9, 8, 7, 6, 5. And then we got the other kids that will not be playing today. That's okay. So, fundamental accounting principle, we would multiply this. It's like we're the Royals manager. I don't know who the new manager is. I don't think it's Ned Yost anymore. And I wouldn't know because, there's no baseball right now. Okay, so let's see how many possibilities we have. Not plus 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5. Look at that. That is the number of batting orders that we could create. 2, 5, 9, 4, 5, 9, 2, 0, 0, comma, comma. 259,459,200. That is insane amount of people, different orders, with only 13 people picking 9 of them. That is just absolutely crazy to think about. Now, if we instead were picking, 500 spots from a possible 1,000 people, it would be really terrible to have to write all of that out and multiply it out on our calculators. It would take forever. So there is a formula. It's called the permutation formula. It's denoted NPR. You might have saw it when we were hitting that PRB button on your calculators just a little bit ago. That means the number of permutations of n things taken r at a time. So in our previous problem, it would be 13 players taking 9 batters to play. So the formula is the number of total factorial over n minus r factorial. So that's the number minus r. Now, the formula doesn't really matter because we have calculators, and I'll show you how to do it on the calculator. So us and 19 of our friends have decided to form a classy lemonade stand. The group needs to choose 3 officers, a CEO, an operating manager, and a treasurer. And how many ways can these offices be filled? So we have, we're going to do the permutation formula, number of choices, and how many are we taking? So it's us and 19 of our friends, so that's tricky. There's actually 20 choices, and we are taking 3 of them. So it's 20 permutations, 3 at a time. So how do you do that? You're going to go to that same PRB button, but we're going to do 20 first, because that's the first number, and then we're going to do PRB, go down to NPR right there, and then we're taking 3. So we have 6,840 different ways that we could fill those officers. Jimba, which is either Jimbo's wife or sister, I can't remember, works for the sitcom television network. You heard of it? I watch it all the time. She has to set up the television schedule for Monday evenings between 7 and 10 p.m. She has to schedule a show in each of the 30-minute time blocks. Jimba can choose from Home Improvement, Seinfeld, The Office, Friends, Parks and Rec, Happy Days, Gilligan's Island, Power Rangers, That 70s Shows, Glow, New Girl, Frasier, and The Good Place. How many different programming schedules can be arranged? So first off, we have 30-minute time blocks between 7 and 10 p.m. So how many shows is that? There'd be a show at 7, a show at 7:30, a show at 8, a show at 8:30, a show at 9, and a show at 9:30. So there are 6 shows that we have to fill, right? Now, how many choices do we have? Looks like we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 shows to choose from. So that would be 13p6, 13 permutations, 6 at a time. Okay. So we just have to type that in. So the big number always goes first, by the way. That's all you have to remember. 13p6. Wow, that is a lot. 1, 2, 3, 5, 5, 2, 0. 1,235,520 different ways that we could arrange those shows. That is insanity. Insanity. Okay. Now, last objective is permutations of duplicate items. So here's an example. The number of permutations of the letters in the word set is 6. They are set, S-T-E, E-S-T, E-T-S, T-E-S, and T-S-E. Now, are there also 6 permutations of the letters in the word Anna? No, because 3, there are duplicate letters, so there's only 3. There's Anna, A-A-N, and N-A-A. The rest would all be duplicates. So, there is a formula for finding the number of distinct permutations when duplicate items exist. The formula is this. The number of permutations of n items where p are identical, q items are identical, r items are identical, and so on is given by the formula n factorial over p factorial, q factorial, r factorial, however many factorials you need for duplicates. Okay, so let's look at a situation. So how many different ways could we arrange Mississippi? And order matters. So how many letters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the numerator is 11 factorial. The denominator is duplicates. So let's start. Our first letter that's duplicated is an I. How many I's are there? There are 1, 2, 3, 4 of them. So that's going to be 1, 4 factorial. The next duplicate letter is the S's. There are 1, 2, 3, 4 of them. So that's going to be another 4 factorial. And then the last letter that's duplicated is the P's. There are 2 of them. So that would be 2 factorial. Now when you go to type this in our calculator, we want to make sure that that denominator is in a parenthesis, or else it's going to think it's 11 divided by 4 times 2 factorials. So we just pull out our calculator, and we're going to type that straight in. I'm going to scoot that over so you can see it just a little better. All right, 11 factorial divided by parenthesis 4 factorial times 4 factorial times 2 factorial. close that parenthesis. So notice I don't need multiplication symbols, that they know what it means. So there are still, even with all of those duplicates, 34,650 different ways, which is pretty cool. So you pause the video, try osmosis here. Go. All right, let's see how you did. There are 1, 2, 3, 4, 5, 6, 7 total letters. And then duplicates, there are 2 O's, there are 3 S's, there are 1 N, and 1 I. So there you go. So you just type that one into your calculator. And it would be 7 factorial divided by, in parentheses, 2 factorial, which is really just 2, and then 3 factorial I know is 6. So there ends up being 420 ways to arrange those letters. Last one, same scenario, one that is maybe a little more applicable. Ellie wants to change her password, that's supposed to be which is Ellie9, but with the same letters and number. And how many ways can she do that? So again, we have 1, 2, 3, 4, 5, 6 total characters. And then how many repeats do we have? We have 2 E's, we have 2 L's, and that's the only duplicate. So we just really need to do 6 factorial divided by 2 times 2, because 2 factorial is 2, which is 4. So 6 factorial divided by 4. There are 180 different passwords that she can make that were unique. Interesting. So there you go. Factorials is your last section. Sadly, we won't get to combinations, which was next, which is another good one to look at, but maybe we can make some time for it next year, all right? You guys, I hope I see you on Thursday. Make sure you come say hi to me. If not, I will see you in the fall. Peace out, Girl Scout.